Hi everybody, sorry I couldn't be there today. We're gonna look at binomial probability. Now, I gave you this worksheet yesterday after the quiz, so I'm gonna go over the answers to this and kind of use this as a segue into the notes that I'm gonna have you basically work on your own. All right. So here we go. So the problem you started with yesterday is you flip a biased coin 10 times. The probability of heads on any one flip of the coin is 3/5. So obviously the probability of tails would be 2/5. All right. And the flips are independent. So one flip does not affect another flip. Calculate the number of outcomes that are possible where you get 4 heads in 10 flips of a coin. Okay, so let's put 10 spots down. 6, 7, 8, 9, 10. I'll number these. 4, 5, 6, 7, 8, 9, 10. Okay, so we need to put down 4 heads in those 10 spots. So maybe I pick heads there, I put heads there, I put heads there, and I put heads there. So I picked the numbers 3, 5, 7, and 8. Okay? So now that I picked those numbers, all right, I'm going to go ahead and I'm going to figure out the number of ways that I could have done that, right? I didn't have to pick those 4. I could have picked any 4. So there were 10 choices, and I will pick 4 of them. 10 choose 4. So 10 choose 4 is going to come out to be 210. Now, it's a combination because it doesn't matter if I pick 3, 5, 7, and 8 or 8, 7, 5, and 3. That doesn't matter. Of course, I could have gotten, a different set of numbers. If I erase these and put a different set, I could have gotten heads on a 2, heads on 4, heads on 9, and heads on 10. Well, that's, 2, 4, 9, and 10. I don't care what order I pick those numbers in either. All right, that doesn't matter. But again, it just matters I pick those 4. Okay, so there's 10 choose 4 ways to do that. Okay. Consider one of the outcomes you counted in part A. So of those 210 outcomes, okay, and here we've got one specific example, what's the probability of this event? Well, it's pretty easy to calculate because we know the probability of getting heads is 3/5 and the probability of getting tails is 2/5. Okay, so we'll have tails in these other spots, right? So we're going to have 3/5, that's the probability of getting heads, to the 4th. And then we will have the probability of getting tails, which is 2/5, to the 6th. And you can crunch the numbers on that, and you get a pretty small decimal. All right, and there's that. So now the question becomes, what's the probability of getting 4 heads when you flip this biased coin 10 times? Well, every outcome that has 4 heads and 6 tails has the same probability. So we can add up all those probabilities, all right, 210 times. So we can add 0.00053 210 times, or, do multiplication. So the probability of getting 4 heads is 10 choose 4, that's the 210, 3/5 to the 4th, and 2/5 to the 6th. And if you crunch the numbers on that, you will get 0.215, okay, or about 21.5%. Okay, so this is a classic example of something that we call binomial probability. So binomial probability. Okay. Binomial means there's 2 outcomes. And usually when we're talking about binomial, we have success and then we have failure. And usually we're interested in calculating the probability of a certain number of successes. So one way that people will write this out is they will have a big variable here, and this is going to be called a random variable. And x is going to be the number of successes. Number of successes in n trials. Okay? So for you to have binomial, the trials need to be independent, and the probability of success has to remain the same throughout the entire experiment. So we want to know what's the probability we have a certain number of successes. So let's say we want to know the probability that x, the number of successes we have, is equal to k, okay, where k is just some number. We will have n choose k. We will have the probability of success, which I'm going to call p, to the k. And then we will have the probability of failure, which is 1 minus p to the n minus k. All right, and it looks kind of awfully familiar to the sort of the binomial theorem, and it's definitely related in a sense. All right, but that is how you calculate a binomial probability. Again, you need two outcomes, success or failure. The trials need to be independent, and the probability cannot change throughout the problem. Okay. All right, so if you go ahead and you try problem D here, what's the probability of getting 7 heads when flipping the bias coin 10 times? Okay, it's pretty much the same thing. Okay, we want to know what's the probability if X is the number of successes that we get 7 heads. Getting heads in this case is going to be considered to be success. So we'll have 10, choose 7. We'll have the probability of success, which is 3/5 to the 7th. The probability of failure, which is 2/5 to the 3rd. And you can crunch the numbers on that, okay? And you will get, oh, you know what? I just realized I wrote down the wrong probability for a previous problem. I'm sorry. So this 10 choose 4 1. I did the math wrong on that. I'm sorry. I was looking at the wrong problem. That was 1148. My mistake. So if you got a different number there and you were confused, my bad. That was 1148. But this one, I was looking at the wrong part of my notes. This one is 21.5% or 0.215. Okay. So that's how you do basic binomial probabilities, okay? Now, question E is a question about something that we call expected value, okay? Now, expected value is really nothing more than a weighted average. Now, it's the weighted average of that random variable that I mentioned before. And remember, the random variable is the value, and this for binomial, it's usually the number of successes, okay? So in probability theory, a random variable is, it's a variable that takes on a certain number in a probability experiment, and each time that random variable takes on a value, it has an associated probability, okay? Now, the way that we kind of write this out is the way we write expected values, we put a big E, and we usually put X here, because we're going to find the expected value of X, and in this case, X is going to be the number of heads, okay? So we want to find the expected value of X, okay? Now, you might have been able to figure this out just by sort of logically thinking about it. The expected value of a binomial distribution like this is actually fairly easy to calculate. If you flip a coin 30 times, and each time your success, in this case getting heads, is 3/5, you might logically conclude that you can simply multiply those two numbers together. You can take the number of trials and multiply it by the probability of success. And so if you did that, you're correct. 30 trials, and the probability of success is 3/5. All right, that comes out to be 18. So if I flipped this bias coin 30 times, I would imagine on average, okay, if I did this experiment over and over and over again, on average, every time I flipped the coin 30 times, I'd expect about 18 heads, okay? Now, that's the quick way to calculate expected value. That doesn't work for every type of problem. Not all expected value problems deal with binomial probabilities. So I want to show you the other way that you can calculate this. And it's a little bit more difficult, but it's important. It's sort of helpful to know. So as I said, expected value is a weighted average. So what I'm going to do is I'm going to make a little table here. All right, I'm going to make it value of X, which is going to be the number of successes. And then I'm going to have the probability of X in the next column. Okay? So if we had no heads in 30 flips, okay, we could calculate that. There's 30 tosses of the coin. We want to pick 0 of them to be success. 3/5 to the 0, 2/5 to the 30th. Okay? Now, you can calculate that number. I'm not going to calculate it, but obviously that's some decimal. If we had 1 success, 30 choose 1. 3/5 to the 1st, 2/5 to the 29th. Okay? 2 successes, 30 choose 2, 3 choose 5 to the 2nd, 2/5 to the 28th, and hopefully you sort of get the idea. I'm just going to put dot, dot, dot here. Eventually I'm going to get to 30 successes. 30, choose 30. 3/5 to the 30th. 2/5 to the 0. Okay? So what I have here is I have a value of the random variable. So this is, again, what I'm going to call my random variable. Okay. And then I'm going to have the probability of that random variable, all right, takes on that value. So if my random variable is 2, then the probability of it being 2 is, as we said, what we calculated there, 30, choose 2, 3/5 to the second, 2/5 to 28. Okay? So how do you calculate expected value when you have sort of a setup like this? Well, as I mentioned before, it's a weighted average. So what we're going to do is we're going to add, so I'm going to put the sigma there for add. I'm going to take all of the values of the random variable that it can take on, and I'm going to multiply it by its probability. Okay? So this notation is just sort of a shorthand, but again, what this means is take every value of the random variable that it can be, multiply it by its probability, and add them up as like a weighted average. So 0 occurs a certain percentage of time. 1 occurs a certain percentage of time. 2 occurs a certain percentage of time. Okay? So you can calculate it that way. Now, since I don't want to add up all 30 of these by hand, I can, of course, use the sigma notation we've talked about before. So maybe I can do, I can use k for my number of successes. All right. I can enter anywhere from 0 to 30 successes. All right. I will do the value of the random variable. So I have to figure out what's the value of the random variable, which is in this column, right? I have to take that value, which is going to be in this case k, and I need to multiply that by its probability. 30, choose k. The probability of success is 3/5 to the k. And then the probability of failure is 2/5 to the 30 minus k. If you plug this into your calculator, you will get 18, same as you did if you did it sort of the shorter way, the shortcut. Okay. Now, I'm not going to go through the entire expected value notes for you, but this is the basic idea. You take the value of a probability experiment, all right, its random variable value, and you multiply by its probability, and you add them all up. Okay. So, jumping over onto the other notes that you didn't look at yet, all right, I'm not going to do all of these problems because I feel like you should be able to do them. I am going to fill out this box with you again, just so you have it in your notes, okay? We'll go back to this and just fill this out real quick. Remember, binomial probability means there's 2 outcomes. Okay, there's got to be only 2 outcomes, okay? You have success or failure. Okay, that's it. We'll let x be the number of successes. Okay. And p is the probability of success. All right. And n is the number of independent trials. It's really important to understand that these trials have to be independent. One cannot affect the other. So then the probability of x successes is, and choose x, p to the x, 1 minus p to the n minus x. Okay. And that's it. Okay. That's binomial probability. All right. So you should be able to do these 3 problems. These should be fairly straightforward. They're just basic probability problems. All right. See if you can figure those 3 out. I will post the answers, not the work, but I'll post the answers so you can check your work with them. All right. So you can look. But I want to actually move on to a sort of a different question that's a little bit different. Okay. I want you to look at problem 4. It's a slightly different twist on what we just talked about. So I'll let you read this over, all right? So we're rolling a single die, okay? We're rolling just a single die, all right? And the die is, again, the outcomes of the die are going to be 1, 2, 3, 4, 5, and 6, just a standard regular die, okay? Find the probability that it takes 6 rolls of a die to get exactly 4 twos. Okay. Now, this is different than me asking you, what's the probability of getting 4 twos, right, in 6 rolls of a die? Because it's telling me that I have to have exactly 6 rolls to get the 4th 2. Now, for instance, if I was thinking about 6 trials here, 3, 5, 6, it might so happen to be that I get, 4 twos on the 4th trial. But that's not what it's telling me. It's telling me that I've got to have a success on the last trial. I've got to get a 2 here. Have to. Okay? So see if you can calculate that probability. I'll give you a minute to figure that out. All right, so hopefully you pause the video and you figure that out. If you haven't, again, pause the video and see if you can figure it out. But here we go. So in this case, the last trial is fixed. I know I have to have a 2 on the 6th roll of the die. That has to be a 2. The variety in where the other 2s come in is really the crux of the problem. I have to get 3 more 2s somewhere in those 5 tosses. So maybe it's there, there, and there. Okay? So in reality, I don't have 6 choose 4. Instead, what I have is I have 5 choose 3. And that's because the last trial has to be a success. Okay? So I need to have 3 2s in those 5 spots. Now, when I look at the probability, though, the probability of getting a 2 is 1 out of 6. Now, you'll notice that there are still 1, 2, 3, 4 2s. So I still have to get that to the 4th power. Okay? And then I will still have failure on the other 2 trials. So that is 5, 6 to the 2nd power. Okay? Now, this is the probability that will happen. It's pretty small here. It's going to be 0.0053, I believe. All right. By the way, one thing that people sometimes will do here is they'll write this as 5 choose 3, 1 6 to the 3rd, 5 6 to the 2nd, and then they'll put that other 1 6 kind of at the end because it is that the last trial has to be success. But ultimately, because of exponent rules, we can combine these into just one. Okay, so it doesn't really matter how you do it. All right, but that's how that would work. Okay, so you can go ahead and try to do problem 5. Okay, it's a very similar question. All right, but I want to kind of write down what this is called. All right, so at the bottom of the notes here, all right, on this page, this is called negative binomial. Okay. So negative binomial. Okay, and negative binomial means you're requiring n trials for x successes. So you know that you're going to have the x success on a certain number trial. Okay, so we'll let x be the number of successes. All right. We'll let P be the probability of success. All right. And N will be, again, N independent trials, the number of independent trials. Trials. Okay. All right. So then the probability, it takes n trials to achieve x successes is, the only thing that changes is you have one less trial, n minus 1, because the last one has to be success, and one less success, because, again, the last one is fixed and has to be a success. P to the x, 1 minus p to the n minus x. And that's negative binomial, okay? So it's related to binomial, but it's a little bit different twist on it, okay? All right, last thing here. If you go to the next page, there is one more distribution. So we talked about the binomial distribution, which we're counting the number of successes in a certain number of trials. We're talking about negative binomial, which is, it takes a certain number of trials to have a certain number of successes. All right, and then there's one more type of distribution that we kind of look at here, and it's called the Poisson distribution. Okay, so Poisson is named after a French mathematician. I know Poisson in French means fish, but it's nothing to do with fish. All right, but this distribution is related to the binomial. Okay, so if this feels a lot like binomial, that's because it's definitely related. In the proof for this, where this formula comes from, starts with the binomial distribution. Okay, so there are times where you have a significant number of trials. All right, and you've seen an average develop over time. Okay, and then you ask the question after you have a large amount of data and a large number of samples of how many, what's the average number of successes you have on a per time period basis. Okay, that's going to be called lambda. Okay, so lambda, this little symbol here, lambda. All right, lambda is the average over some time period. Okay, so the average number of successes, quote unquote, over a time period. If you want to know what's the probability that you get a specific number of successes given that average, okay, you can use the Poisson distribution. But this is only if you know the average over some time period, okay? And it's definitely related to binomial, all right? We're not going to get too much into that, but the proof of where this formula comes from is from the binomial, okay? So, the Poisson distribution, the probability of having k successes, okay, is equal to e to the negative lambda to the k over k factorial. Okay, kind of crazy looking. But remember that lambda is the average over some time period. E is that natural number. So remember, E is 2.718 or whatever. All right, and k is the number of successes that you're looking for. So using the Poisson distribution is fairly straightforward. You just have to make sure you get the lambda correct. It's usually the only thing that can cause any trouble. Okay, so let's take a look at problem 6. The average number of homes sold by Acme Realty is 2 homes per day. So you would know this after looking at a large amount of data for a long amount of time. Okay, so you have this value. You know what this average is over a long period of time. Okay. What is the probability that 3 homes will be sold tomorrow? Okay, if that average holds. Okay, so, all right. First of all, lambda. Lambda is the average number of homes sold. Okay, and it's important you sort of put the units here because that can matter. All right, you have 2 homes per day. Okay, that's our average. Now, it says, what's the probability that 3 homes will be sold tomorrow, which tomorrow is 1 day. So this lambda makes sense. If I had said to you, what's the probability that 3 homes were sold in a week? Well, in a week, I would imagine the average would be 14 homes a day. So you have to match your lambda to the unit that you're looking for. Okay. So we want to figure out what's the probability that we have 3 homes sold tomorrow. Okay, pretty easy just to plug this in. F of lambda, in this case f sub 2, all right, of 3. That's kind of the notation we use for this. It is equal to e to the negative lambda, negative 2, all right, times 2 to the third over 3 factorial, okay? And that comes out to be about 18%, okay? So that's basically it, okay? Now, again, you might be wondering, well, how does this relate to binomial? And it definitely does relate. Okay, so if it feels very similar, there is a connection there. why don't you go ahead and try to do problem number 7, all right? See what you can get on that. Again, I'm going to post the answers to that so you can kind of take a look, but I feel like you should be able to sort of figure that one out. Okay, I'll post the answers for you. The only other final thing that I want to talk to you about here is a little bit more with expected value. Okay, so I'm going to go to the other note sheet, the expected value note sheet. And I just want to take a look at this real quick. Okay, so expected value, when we did it before, was we were looking at the expected number of successes. It doesn't have to be the expected value of a random variable. The random variable doesn't have to be the number of successes. Okay, so the random variable can be any value that a probability experiment takes on. Okay, so here's an example. In a game of chance, a player rolls 3 dice and gets rewarded according to the number of 6s that come up. And the rewards are $5 for 1 6, $10 for 2 6s, $15 for 3 6s. The 3 dice are rolled. What's the probability of winning $15? Okay, so you should be able to calculate these probabilities. So I'm going to give you a second to calculate those probabilities. Okay, so I'll give you a second to calculate that. All right, that's binomial. So go ahead and calculate that. I'll pause the video and go ahead and do that. All right, so hopefully you pause the video and you calculated the probability. So to get 3 6s, okay. So I'm going to let X is going to be the amount of money. So I want to know what's the probability that the amount of money we get is 15. Okay, so we're going to roll the die 3 times. So to get $15, we got to get 3 6s. So it's 3 choose 3. All right, and then it's 1 6 to the third and 5 6 to the 0, obviously. So this is 1 over 216. The probability of winning $10. Well, to get $10, I got to get 2 6s. So 3 choose 2. All right, I have 1 6 to the second, and then I'll have 5 6 to the first. And that'll be 5 out of 72. What's the probability of winning $5? All right, well, $5 we got to get 1 6. 3 choose 1. 1 6 to the first, 5 6 to the second. And that will come out to be 25 out of 72. What's the probability of not winning anything? Well, different ways you could calculate this, but the probability of winning $0 is you have no successes, right? You get no 6s. 3 choose 0, 1 6 to the 0, 5 6 to the third. And that is the most likely outcome here, 125 over 216. Okay. So, all right, so we've got that. All right. All right. Now, question E is really the only question I want to go over with you. You should be able to do the rest of these. When we look at this now, we want to find what's the expected winnings for this game. Okay, so winnings is the random variable. Okay. So X is our winnings. All right. And we want to calculate what's the expected value of X. Now, as I told you before, it is the value of the random variable times its probability. It is a weighted average. What percentage of the time do we win $15? Well, 15 times 1 over 216. All right. 10 times 5 over 72. 5. 25 out of 72. All right. Plus 0. Okay. And again, in this case, 0 is not going to affect the outcome, but I'm going to write it down anyway. All right. And there it is. This is the expected winnings. So we will win $2.50 if we play this game. Okay. That's the expected winnings. Okay. So that's the basic idea of how you calculate expected value. Okay, so expected value is simply a weighted average. It's a weighted average. That's the one way that, probably the easiest way to think about it. The expected value of X is simply all the values that the random variable can take on times the probability that it takes on that value. And you add them all up. Okay. So in this game, we would expect if we roll the die, All right, we expect to win $2.50. Now, a lot of times in gambling games and such, you don't get to play for free, right? Like it costs you money to play. So if you look at the next page, it says, well, if it costs you $3 to play this game, what would be your expected return? You should be able to answer this pretty quickly. Okay, if it didn't cost you anything, we know we would win $2.50 per game. If it costs us $3 to play, you can hopefully do some very basic mental math there. We'd take $2.50, but we would have to subtract the $3 it cost us to play, and we would get negative, all right, $0.5, right? All right, 50 cents. So you can calculate that way, all right? Or you can calculate it using a different random variable. So just to show you this, because this will work out the same way, you can let X be your net winnings. Okay, instead of just how much you win, you can take out the $3 for each outcome. So if you want to find the expected net winnings, I should say, we'll do the same probabilities. Okay, so we have basically the same calculation. Let me zoom out here. So it was 15, but it's going to be 15 minus 3, 1 over 216. We're taking out the $3 that we cost to play, plus 10 minus 3, 5 out of 72. All right, 5 minus 3, 25 out of 72. And here's the most important part, I'd say. 0 minus 3. There's your losing hand, where you lose you lose money on that hand. All right, and you get 125 over 216. If you crunch the numbers on that, you will get exactly what we got before. All right. Sorry, that's not right. You will get minus 0.5. All right, minus 0.5. Okay. So that's the net expected value. Okay. All right. So that's it. Okay. So I'll let you kind of work through the rest of these. They're pretty much all the same thing. Okay. So I'll let you kind of work through those. I'll post the answers on Canvas. But hopefully that gets you a good start on that. Your homework deals with binomial probability and expected value. Okay. Should be back on Monday. Sorry I'm not feeling good. If you have any questions or anything, feel free to send me an email and I'll try to get back to you. Take care, and I'll see you Monday. Bye-bye.